Hi guys, good morning everyone. It's lovely to see all of you here today. I've been sure you're having been hearing lovely people giving amazing talks. We're going to try our best to match that expectation. So, my name is Mohtesham. Please call me Mo.
And my name is Abhishek.
We both are doing cybersecurity analytics at this university. And today we're going to be talking about one of the most pivotal attacks in the history is meltdown, Spectre and meltdown attack, which was on every computing modern architecture you can think about. And I run the Cybersecurity Society in my free time, and he's also my society member. So guys, picture this, the Gulf War just started, right? And it's 1991, it's been 5 months, and everyone's burning question is that when is the American government going to take the next attack, or when is something going to happen? Everyone's, interested in this question. Nobody knows, right? Everyone's trying to dig in. What do you do to get this information out of the Pentagon or the White House? What do you think is possible? Hire the best social engineer, try to persuade someone after like a drink, after a happy hour or something, or maybe get the best hacker in the world. Unfortunately, none of this works. The solution is very simple, to be honest. And meet Frank. He's a Domino's franchise owner across the whole Washington area. And he discovered a simple pattern. He discovered that, before I say what he discovered, he knows exactly when the date of any invasion or anything is going to happen. How does he know this? He observed a simple pattern, which says that, if you look at this graph, at 10 o'clock, the White House ordered 55 pizzas instead of 5 pizzas, and the Pentagon ordered 101 pizzas instead of 3 pizzas. So he noticed this pattern and he was like, hold on a minute, this happened once, this happened twice, this happened twice. It predicted the Iraq invasion, the Panama invasion, then the Tunisia invasion perfectly. And he knew this. And the Pentagon had no idea. This is what we call side channel attacks. These are something which is like a pattern which is easily recognizable. And in this example, I'm relating that to pizza. So what are side channel attacks, right? Side channel attacks doesn't have to be, the most, breaking into some encryption system or something. It's like observing some kind of pattern, which is frequently happening. So you can use that pattern to, break into that system, right? So there are multiple types of side channel attacks. There are timings, power usage, cache behavior, electromagnetic. The one today we are going to be focusing on is the transient execution attacks, which consist of the Spectre and meltdown variant.
So this is how it impacted the whole world. Can you play the video?
Tech firms are rushing to patch a security hole that is affecting billions of computers and smartphones. It's caused by 2 major flaws in computer chips called Meltdown and Spectre. They can allow hackers to steal sensitive data like passwords or see what tabs you've opened on your device. Researchers say Meltdown affects only chips made by Intel, while Spectre exists in almost every computing system. Let's find out what this means for us.
So as you can see, it was affecting the whole world and everyone was worried about it. And so it was the global impact was like every device from iOS, Linux, Windows, Apple, everyone was affected by this, and even the cloud infrastructure was not safe.
All of them?
Yeah, all of them. So, and in my opinion, the industry, tech giants like Intel, AMD, Microsoft should come together and do the fixes, patches on the day 0 instead of waiting it and delay it.
So we're going to reenact a situation here, right? It's going to be a very simple thing. We're going to reenact how permission checks works, right? So I want this book.
Yeah, show me your ID card.
Here you go, my ID.
Okay. Yeah, it's fine. You can have the book.
Thank you so much. I need this other book.
Yeah, it has a different type of ID card.
Yeah, I have this one.
No, it's not. I want this one.
Yeah, well, you can see that's how permission check works. This is on a theoretical level. We think that if there's a permission, it's access, they have access to the information. If it doesn't have permission, it doesn't get access, right? But on an architectural level, this is not true. We'll look at why. So let's dive into the actual topic, which is the Spectre and meltdown, right? So what is meltdown? And I'm going to give you a very easy explanation. You can see this is a user space and this is the kernel space, right? Wouldn't it be easier if we could somehow bypass that permission check wall or this wall and get to the operating system? Woo, like Houdini, right? It just disappeared. How do we do this, right? There is something called in order and out of order execution. When you write a line of code, right? The instruction set get executed line by line, which is like a bit slow for the CPU, but Here comes speculative execution, guys, fixed for everyone. What it does is, let's say you have two loops in if statement. The first one is an add operator, the second one is a division operator. The add one will be done quickly, the division will take some time. So the CPU will be like, well, I don't want to waste that time waiting for you to solve that problem. Let me execute everything under your instruction, but not commit anything, right? So it executes, computes this answer, keeps it in the cache, but doesn't commit it. Then when it learns that it made a mistake, it, rolls back, but this information that was bypassed, the permission check which was bypassed and this was kept in the cache, remains in the cache. So hold on to that thought for a minute. You bypass the security and you bought some valuable information without checking any permission of that, and you stored it in the cache. Just hold on to the thought.
And now, unlike Meltdown, Spectre isn't a single attack. It's a whole range of different attacks. It basically works by tricking the running program into accessing the data that it shouldn't. It's similar to Meltdown, but for example, let's say I'm working in the office for past 10 years, and after one of my job is to open the door for the delivery guy to everyday come in and go out. So it's been, I'm pulling an overnighter one day and it's 3 a.m. and I saw the guy. I didn't think twice, I just opened the gate. And after a few minutes, I realized it's 3 a.m. He should not be here at this time. So, but during this time, he stole a package and hid it in the washroom. And
he took some package out of the privileged area and kept it somewhere else. And then
this package should be think as the data that is passed to the cache memory without even checking error.
It's basically like in this example, if we get more technical, that's a very easy example, right? But it's basically like, it's the same thing. There's something called the branch predictor, and we give it, like, for example, in this example, we run a program, we run this for statement 1 million times, and we say A equals to this, A equals to this. Eventually it will be like, oh, A is definitely equal to this. So it just skips the time by predicting all the time that, oh, A always equals to this, because it's more efficient, right? So once what happens is, after the 1 million and one time, we will say A equal to something else, but it'll be in the false notion that A equals to this. And it'll execute that temporarily, getting the information out of the privilege area without checking the permission check, if it's allowed to go there or not, puts it in the cache, and then after that, it'll be like, hold on a minute, this is not supposed to be accessed. Okay, let's roll back. Let's not give the user this information, but it keeps it in the cache. Again, just like Meltdown, Spectre also does the same. Gets it out of the system without any permission checks, put it into the cache, and then I'll explain what happens later, but that's basically what this permission is doing. Getting the information out, keeping it there. Right?
Yeah. So, it's the job of LRU to keep the cache memory clean of the processor. So, it aims at to keep the most frequent access data in the cache, and by removing the least used data out of the cache. So, it works by tracking usage. Basically, it tracks the thing that is accessed by the user more time and tries to keep that data in the cache, while and also it moves the data to the front of the list so it can be accessed by the processor much faster than compared to other data.
Basically, like when we removed the sensitive information kept in the cache. This replacement policy wasn't there. This was the fail-safe, which was like, oh, we'll get rid of that sensitive information from the cache later on. But that later on, unfortunately, people have evolved and realized that we have enough time to use this, to use some kind of, for example, timing attack to find the sensitive information, get it out before this replacement policy throws it out of the cache. So because of this, the LRU was there as a fail-safe, but it did not work as intended because, humans likes to, somehow find that exploit, let's get in there, right? But, yeah.
So let's dive into the CPU itself. So, for example, I want to print the value 5. So, I will ask my CPU cache, and the value 5 was not in the CPU, so it got cache miss in this case. Then the CPU will request the RAM for the value 5. Then the RAM will respond with the value 5. Now the value 5 stored is in the cache itself. So, the next time I call the value 5, it's a cache hit in this case, so I get data much more quickly because there was no RAM access. And the previous one, because the RAM access occurred, it was slow as compared to the much faster one, the cache hit. So as we can see, it's the memory latency chart. If the cache is hit, then the data is retrieved under 100 CPU cycles as compared to the cache miss. it takes around 750 to 1000 cycles to retrieve the data from the memory to the cache memory.
So if you look at this clearly you can see that this is a cache hit and that's a cache miss. And this was enough information for
side channel time attacks to figure out what type of information is in the cache and not in the cache.
Yes.
So this is the different type of classification that are under Spectre and Meltdown. As you can see, these are a lot. It's
ongoing. It's unfortunate, but it keeps evolving. They keep finding new variations to, keep exploiting this attack surface. So why did this happen, guys? In the end of the day, we don't want to blame the consumers. We don't want to blame the manufacturers, right? But let me ask you this question, right? If I asked you, would you buy a slow computer? Would you buy a fast computer? You're going to say you want to buy a fast computer, right? But if I lace that question with saying, do you want a slow, secure computer or do you want a fast and, slow computer? You would say, well, let's blame the manufacturer. You need to give me a fast and secure computer, right? So the manufacturer is put in a position where they don't have enough Intel to generate some kind of secure system, where they are forced to find some kind of, workaround. So all of this AMD, all the Intel, fund companies, right? All of them decided, let's use speculative execution, increase the, percentage, for example, from 3 to 30%, which is a huge improvement in performance, and keep using this strategy. Unfortunately, the LRU failed and, we are here where we are right now. So it's because of psychology of speed and cost. And the more fast it is, the more money you can make as a manufacturer, right? And there was a fail-safe, like we spoke about, but it was not good enough. The replacement policy was not good enough. Yeah.
So these are some countermeasures that were given by CPU vendors to fix the Spectre and Meltdown. For the Spectre, the CPU vendors provide fixes that fix the vulnerability in Spectre Meltdown execution mechanism, and they use a technique called repo line. That's a compiler technique that prevents misprediction from any indirect branch, and it reduces the Spectre risk, Spectre style attacks. And for the Meltdown, they use the technique called KPTI, stand for kernel page table isolation, and in this technique it isolates the kernel memory from the user space memory. And another example was that they also gave the microcode update for the CPU to block the Meltdown exploit from occurring.
So for the hardware, this is some considerations for the CPU designers. Obviously they're not here in the room with us, but they could use some kind of techniques like cache randomization, scatter mirage techniques. These are techniques to make the pattern of the mapping lines that we're trying to find more unpredictable by adding some kind of noise or something. By making it more unpredictable, the cache line, and moving it to different cache lines, we can make the pattern very unpredictable that the timing attack will be useless. So this is the technique, scatter mirage and cache randomization. Yeah.
So there should be a fine-tuned balance between performance and security, as Mohtesham has told you. After the vendors have applied the patches for the Spectre Meltdown, there was up to 20 to 30% slower with the patches, and with the new system was impacted by, let's say, between 5 and 10%. Reason was the patches, as I told you. The main was KPTI, as it requires to reload the memory during the kernel is accessed. So the main lesson learned from this should be, there should be a fine line between performance and security, and the vendors or the creators of the processor should consider re-evaluation design priorities, and they should build the processor from ground up scratch so they can introduce security things more as compared to the just more raw speed. And there should be a continuous vigilance of this, as this was for left unnoticed for decades. So in conclusion, Spectre Meltdown was a pivotal moment for all of us in the cyber landscape, and it prompted re-evaluation of the design priorities and reinforced multi-layer security strategies to safeguard against evolving cyber threats.
Thank you guys so much for listening to us. Do you guys have any questions? Thank you so much, guys. Thank you for your time.